My presentation will be about the electrical properties of biochar and biochar-based composites. So, what is my main point? My main point is that we discussed a lot with different companies in the last months, in particular from the automotive sector. And several of them, they just require something that they can use to it's sad to say that, but it's true, to greenwash them for their customers. For example, a company close to my university just asked to us to produce some actuators that are based on sustainable materials able to be used instead of copper. And that kind of discussion is quite happened quite frequently to every one of us, I think, but can be a great occasion to just stress out the potentiality of biochar and move to the proper greenwash approach to something more consistent with a real action and with a real impact. So one of the fields that we found that it is quite promising is just use biochar as very conductive filler, just to replace what is used now for producing composite with electrical properties. And that is easy to be figured out because basically it's carbon and carbon can be conductive. The point is, can be conductive enough, can be produced and standardized, and if it is possible doing that, there is a trade-off somewhere in certain point between the thermal treatment that are needed for use biochar as conductive filler and its cost, because this is the other problem. If I'm going on the market and try to buy a conductive carbon, I'll buy carbon black, the Vulcan C type. That is the more common one. It is the one used for batteries and energy storage application. Can we match that specification, and how we can do that? So this presentation is about this kind of stuff. Try to figure it out how to produce conductive biochar, how it works, how can be optimized, and how we can use it for doing something that is high added value materials together with some interesting from who is going to use it. So why composite? For the simple reason that composite market is huge. It's billions of dollars. Even if with the crisis, even if with the changing of the economy, it's very huge. And more important, if you are looking to the composite market, you are seeing that the major amount is represented by plastic-based composite materials. And in particularly, the great amount is represented by tires, by structural composites, by polypropylene. So all the plastics that is barely used in electronics is basically a composite. And all of these materials can be look with the critical eye and see where are the criticality for their impact on the environment, sources, on the sustainability of their use and end life. Among them, the conductive composites represent an interesting, small but lucrative sector. Keep in mind that all the automotive sector is moving from the classical cars and vehicles to something that is smart and smart and smart. Keep in mind a Tesla model. In a Tesla model, you have basically a screen and buttons. So all that buttons, all the actuators, all the things that you are seeing, in principle, can be replaced with conductive composite materials, and in particular, biochar-based one. Here you are seeing the basic approach of carbonization of biomasses. You start from the beginning, releasing water, start to degrade the polymers. At a certain point, you are starting to graphitize the carbon. And here is the trade-off, the 600 degrees. you need a very high temperature to produce a biochar that is conductive. And 600 degrees is also a trade-off from the plants, because when you are figuring out a pyrolysis unit that is just producing biochar in continuous mode, and you are moving a corkscrew or a rotary kiln and so on, well, the cost for doing that for temperature above 550 degrees are increasing exponentially. But at the same time, the cost price the biochar produce is increasing. So if you discuss with someone, say that you can fully graphitize biochar at 2000 degrees, it's not completely true, because again, a little bit more science on that, but if you start to heat it, you reach a point where you cannot stress it out the graphitization process. According to the pioneering study of Rosalind Frank in the middle of the 20th century, biochar is not a graphitizable carbon. Can be highly ordered, similar to a graphite, but it will never be a graphite. So for certain kind of application, conductive biochar is not the best, for the simple reason that, as you can see here, the intrinsically complexity of the starting biomass prevent the fully reorganization in the proper graphitic stuff. So there are some kind of application where it is required, for example, a very pure graphite where biochar cannot be used. But for the other ones, where a carbon soot, a conductive carbon soot produced from acetylene can be used, biochar can be used. So here some theory. So as I said, I'll try to be very quick on this. What we are doing in this field, we are doing two things. We are trying to improve the classical conductivity, the one that you can measure simply with a multimeter, but we at the same time try to use it for those kind of application where you can use a lot of biochar because it can contribute to the decarbonization process of, for example, construction sector. At the same time, introducing some properties binded to the conductivity. So I'm shielding. Keep in mind that in the actual society, if you want to keep in your home your Wi-Fi signal and you don't want that your neighbor just use it, you need to put a barrier for that. And cement alone is not enough for time. So we are working on a project, a European project in collaboration with the National Research Council, where biochar is used for not structural, but for structural building materials for shielding the electromagnetic frequencies. And we saw that we need a highly conductive biochar for that, but you are seeing that. So our very first study in this field was a benchmark study. We take a commercial biochar, just one of the one that Prof. Mazek is producing in Edinburgh, and we compared it with carbon nanotubes. And we saw that we can obtain something that is quite similar. Of course, we use a lot of biochar for doing the same thing. But if you keep in mind that properties should be balanced with carbon sequestration and the overall impact of this process is something that can be interesting. For a more scientific point of view, we saw that biochar creates aggregates inside the polymers, creating bridges that can promote the conductivity. It is acting more like graphite chips. They're generally called potatoes because they are potato shape. But the point is, it is acting in this case as micrometric carbon. It is quite interesting because a micrometric carbon, so a carbon that is in particle size around 1-2 microns, can easily match a nanocarbon like a CNTs from the conduction point of view. And here you saw that also temperature, as I said, play a great role. Because if you are just moving from 650 up to 750, and the electrical performance, both in frequency, so under microwave radiation and under simple compression, just to check the conductivity under stress condition, you see that 100 degrees matters a lot. But this temperature is not enough for certain kind of application. It was, again, a very old study, 5 years old now. But that study helped us to understand that we should stress the temperature point. And here, we use tea leaves in this case, we reach 1000 degrees. We saw an interesting thing. We saw that at a certain point, biochar conduction resembling the one observed in metals. So there are some grains of biochar inside the biochar particles in biochar chunks that show metallic behavior. And this allows us to produce a polypropylene that was conductive, while the same field with the carbon black didn't show any properties from the conduction point of view. So we saw that 1000 degrees is the real trade-off in temperature to say, okay, this biochar is a conductive one. There is a threshold there for any kind of biomass that we saw, with the exception of mass, but so later. So 1000 degrees is the threshold temperature. Below, you have a conductive biochar that is not so performing. At 1000 degrees, you have a conduction that is appreciable and quite high. 1000 degrees means a lot of efforts to reach that. But if you do not think to traditional biochar pyrolysis approach, the fast pyrolytic plants, fast pyrolytic units, but the autocombustion setup, you can easily reach this kind of temperature. So nowadays, with the autocombustion process based on plants, we can think to reach this temperature in a profitable way. Same thing for other kind of more exotic ones, like cotton. We study cotton because it's basically cellulose oriented. And as you can see, we can obtain similar carbon fibers. Also in this case, we observe a metallic behavior. But in this case, we saw also that we can use them, even if they are quite fragile at this temperature, that we can use, let's say in this way, a tissues-like biochar-based material. So we make a net, we preserve the net, we pyrolyze it, and we use it as conduction bed. Of course, even if native properties of the materials matters, as you can see here, carbon black and the neat biochar produced from coffee show more or less the same conductivity, even if carbon black is a little bit more performing. Inside the composites, the micrometric structure of biochar is an advantage because a more homogeneous distribution inside, while carbon black is tending to create island, and this is preventing a lot the conduction. So if a player in the automotive sector just came to you and say, I want something that is cheap, is conductive, and it is not containing metals, you cannot propose them carbon black. They tried, and if they came to you, it means that they tried and they failed. And biochar represented a solid solution, at least in our project experience doing that. Of course, this is laying in a proper physical explanation, and in particular in the available traveled path. Micrometric particles means that you can create bridges, as I said earlier. And these bridges, as you can see here, follow the opposite trends of conducibility. You create just a preferential pathway in your composite with your biochar particles on micrometric scale. And this is one of the great things that you cannot do with carbon black. Carbon black is the reference point for any kind of composite study, but in this case is outplayed. And here we are going to one of our recent investigation. It's a quite comprehensive one. We proved that temperature matters, and the threshold of the temperature was around 1000 degrees. We proved that the structure matters. Particles with the micron size are better than nanometric particles, was unexpected. And here you can see that pyrolysis condition doesn't matter. What does it mean? It means that if you are moving from a slow pyrolysis to a fast pyrolysis process, you are not affecting so much the performances of your conduction biochar, conductive biochar. Here you can see that slow and fast pyrolysis practically show the same properties, but the temperature is more important. So you can heat as you wish till you heat enough. And this is the reason that I should stress, and I've never stressed enough, auto-combustion based process, the one that you are just sealing and just heat it up, are the best solution for production of high conductive biochar. And this is an objection that I said a lot. If you just not running all the process in a proper inert atmosphere, and if you are running out of combustion process, the functionality, the oxygen that is remaining in your biochar is affecting the conductivity, and the answer is no. Here you can see some XPS and some Raman analysis of the carbon treated in proper auto-combustion system. And you can see even if the oxygen is present in all of them, the conduction is following the same path that was expected. It means that basically you can have oxygen preserving the conductivity, and combine the things, you can have a solid solution for the production of biochar treated at a very high temperature without compromise too much on the cost of the material. Of course, you can trick the overall process because you can pair the electrical conductivity with magnetic properties. Here we used olive residue, just tailoring heat with iron particles for producing a conductive biochar that is showing also magnetic properties. And we move these magnetic and electric properties to composite. So we obtain a composite that is at the same time showing magnetic and high conductive properties. So you can have smart materials in this way, tailoring heat, using the appropriate temperature, and so on. But of course, we can also combine this approach with the more sustainable ones. For example, this one is the same, just for concluding, same trend that you saw before, increasing the percentage of biochar. You can just increase the conductivity. And if you are increasing the amount of tailoring agent, in this case iron, you are not so decrease the conduction. But if you're replacing iron with red mud and try to cut off the impact of your material, you can obtain the same properties. And it is quite interesting because you can have a smart material with high conductivity with the increment of crystallinity, so the increment of conduction of the final composite, using red mud that is quite hard to manage and it's a pain just to dispose. But here we can just use it as mix with, in this case, hemp, and producing a functional biochar that has a cost that cover the process. So it's quite interesting if you are thinking to reshape certain kind of applications. And in the end, I'm finish with this one. We obtain values that are quite on the state of the art of the more high cost and high performance fielders. ranging from carbon nanotubes, carbon fibers, unidirectional prepeg, and so on. So technically, biochar can be used as conductive for the production of conductive composite. Conductive composite that are all around you, and conductive composite that are a request, because we shift on this kind of research because we believe that it's interesting, but because there was a great interest for our industrial collaborators in this particular field. And there are plenty of parameters that you should keep in mind, as you saw, but tuning all of them, you can have something that is astounding, let's say. So I think with this, I finish. And if there is any questions, here I am to answer. Thank you for your attention.
Thank you, Mathieu, for your presentation. As always, very technical. So let's see about the questions that come up. My question would be, the first one is, so we know it can work. How about upscaling this? So how homogeneous or how much variation do you see in biochars?
Okay, what I can say on that is it's covered by NDA, but more or less it's something that I can share. It's more homogeneous than I thought, because in the very, very first place, I was just thinking, okay, we start to eating up, as I told you, the combustion approach, mixing with iron, and I was expecting just to take the stuff apart from the reactor and finding something that was good, something that was not, something that wasn't. I was wrong. It worked. It worked a lot. So the batch after batch retain a great reproducibility. And if you ask an explanation for that, I don't know. I cannot provide that because I'm struggling to understand that, but it worked.
I mean,
and we are discussion about 100 kilograms for each batch.
Okay. And okay, I take the question from Agnieszka. Have you seen any variation between different feedstocks? And can you say what is the main parameter? Is it the ash content, was the question?
Yes. If you are using biomass-based materials and moving from 1 to 3 point of weight percentage of inorganics, it's not a problem. If you're using rice husk, or if you're using any kind of mud, any kind of them, in that case, you are seeing differences. Because if you are increasing temperature, the point is the inorganics acting as a catalyst, they're breaking everything, and the carbonization is not super fast. So rice husk, it's not the best option. Any kind of mud, it's not something that you want to use for ballistics.
And okay, Vera, interesting presentation. We used carbon nanotubes for controlling electrical conductivity. Do you have conductivity, I guess, versus bulk density of the biochar data for coffee biochar?
Yes, it was a little bit nightmarish because for doing that, you should powder it and try to make a solid chunk just to remove all the voids and have some reliable solution. We also try to measure as a grain particles, but the fractal structure of the coffee was a little bit hard to modeling, but yes, we have them.
Karen was asking, did you observe any impact of heating rate on the
No.
electrical conductivity? So you basically, so you can go up as fast as you want.
We explore from 2 degrees for minutes up to 50 degrees per minutes. If you are aiming for the powder, there is any kind of difference that you can see. If you are aiming for a solid chunk of biochar, there is a nice work of Prof. G about that. You should stay low, 0.1, 0.5, at least 1, at maximum 1 degree per minute. But only if you want a solid chunk without cracks inside of biochar. If you want powder, heating rate doesn't matter.
And did you try to to upgrade existing biochars? For example,
Yes.
okay. So that works as well, or?
Yes, the problem is if you want to do that, you should be sure about the composition of the stuff that you're working with. We work with plenty of them, and we saw, for example, if you are processing a 700 degrees biochar, I can just heat it up at 50 degrees for minutes till 700 and keep at 750 or 800 and so on. That's not the problem. If you are working with center kind of biochar that are mixing in quality, you should keep in mind that you are working with something that is mixing in quality. So probably in that case, it's not an upgrading, it's just a reprocessing. So this is my experience on that and the trade-off that you should put inside.
Okay, but in theory, you can take a
Yes.
commercial char and
Yes.
upgrade.
Technically, you can see this process as a post-processing that you can put downstream to your reactor. You
Okay.
have your reactor that is working at 400 degrees and a static oven that is just annealing your material.
Yeah, because I think that's one of the approaches to go to higher temperatures. And out of curiosity, because you talked about micron size of biochar, anything you can share on the best way to industrially grind biochar?
No, it's covered by NDA. We are struggling in the last month for doing that on different kind of size from 0.5 up to 10 microns in a controlled way. Technically can be done, but it's a pain. It's a real pain. It's something nightmarish from the starting to the end. It can be done, but it's not something that I'd like to do. Let's say